Okay, the differential pressure controller. Oops, no, that's not at all what I wanted to write. This is why it's going to take so long. Because it's not a differential compressor. Yeah. Differential pressure controller. All right, that was the second controller. So we talked about the first one. That is, its job is to read the density and give max power. So it's the more power one. All right, differential pressure controller. So one side of bellows is connected to upper deck. Other side connects to manifold pressure. I said bellows. I have to think about that one, if it's a bellows or not. Let's see. Yeah, I'm kind of thinking so. Spring pressure holds valve in NC position. What's NC stand for? And that would be, NC means normally closed, which means?
Spring closed.
So it's closed. So if it's closed, is that oil flowing or blocking? What?
It's a spring.
You got to keep it straight. So normally closed in the density, in the controller, in the differential controller. So the spring pressure holds the valve in normally closed. Closed means oil flowing or no oil?
No oil.
Okay. No oil flows. That means turbo wastegate is then open or closed?
Closed.
Wastegate is closed, which means turbo on. So if pressure differential from upper deck pressure UDP to manifold pressure MP exceeds a set limit, valve opens, bleeds off oil. Wastegate does what? Opens. Turbo slows. Because it's not getting off, we'll say slows. And that set value is somewhere between 2 to 4 inches mercury. So it's not a lot. I'm not going to write all this next part because we already covered it. But if you want to write all this down, just write down everything I say. Okay, operation, which you already went through. At part throttle, so this is part way open, part throttle, density controller is closed. Why?
It's not at max power.
So it wants
More power.
more power. All right. So differential, let me see, density is closed, asking more power. Differential controller over here senses the difference between the two and says, you got enough. You got 2 to 4 inches difference. That's more than enough, right? So differential controller senses the difference between upper deck and manifold due to the larger differential across the throttle plate. This allows differential controller to adjust the wastegate. So now the wastegate's going to open a little bit. Let exhaust gas goes that way. And that helps to prevent what's called bootstrapping from this, pick yourself up by your bootstraps, which is very difficult. You just kind of reach down and like grab it by your boots and try and lift yourself up, and it doesn't work so well. But I'll write down what bootstrapping is in a minute. But it's basically where it's sort of a runaway. It's very sensitive and runaway. Let's see. As throttle is opened, we're going to open the throttle now. What's going to happen to the differential between the two?
Goes down.
It's going to want to equalize. So the differential pressure controller is going to
Close back out.
close. It's got to block off the oil. So that is going to cause the wastegate to start to close, which will start to give us more boost. It will do that up until we get to full throttle. So now we're all the way at full throttle, and the differential pressure controller is saying, you only got an inch difference here. So what is the differential going to want to do at full throttle all the time? Stay closed. And so now we would just continue to have this runaway, except for density controller now comes online. And when it reaches its maximum density, it opens, bleeding off oil, controlling the wastegate. That's it. All right. Let's see. That was very good, if you got that. That was operations that I just covered, which we covered already. Problems. Let me see. One problem is turbo sensitivity. You have to be careful what you say around them. All right, one is, let's see, problems. Throttle sensitivity. No, I didn't want to write turbo sense. I'm sorry. Been one of those long days. Too much of a hurry. Throttle. Throttle sensitivity. Turbos respond slowly. They're a little slow to respond. You got to think about how this whole system works. It's not simultaneously. Things got to happen. And we're going to be looking at a lot of things, I think, from here on out that takes a while for things to happen. So we open up the throttle. I just opened it. Well, now that opened up. And so differential pressure controller says,
You need some more.
you don't have enough differential. We got to close off. So that close off. You got to wait for the oil to back up, start pushing on this piston. It's going to take time for that piston to move and move that throttle plate, right? And so meanwhile, the engine's trying to go. I mean, I've already told it to go. It's trying to go faster. Boost has taken a while. So that's got to switch. Now you got to run the air down the Y gate over to the turbine wheel. Turbine wheel's got to start spooling up faster. And then we get more boost from the turbine, the compressor. That all takes time. I mean, probably not as long as it took me to explain it, but it all takes time. So you do end up with this system that's a little sluggish, and that causes problems because you add too much throttle, like, oh, too much boost, now I got to back it off a little bit. So that's the sensitivity you get. You can't just put it in a spot and then it's like, oh, it'll be fine. It takes a while. So, so turbos respond slowly. Pilot opens the throttle, which establishes a new differential pressure. Differential controller senses a change and repositions the bleed valve. The new bleed valve setting changes oil flow from the wastegate. I'm not going to write all this because I just said it. Wastegate changes position and increases the turbo speed. Increased turbo speed increases the turbocharging, which increases upper deck and manifold pressure. This causes the differential controller to move, which starts the process all over again. So it's in this constant loop of sensing and changing. Meanwhile, you as a pilot, you're watching a manifold pressure kind of move around. So, let me see, throttle sensitivity. I don't know why this is out here. Whatever. Bootstrapping. Let's see, if the differential controller was not operating, any increase in throttle would cause an increase in turbo speed. So I remember we talked about the other system. Without the differential controller, you've got, say, 40 inches on one side and you've got 10 on the other. And so you open the throttle just a little bit and you get way more air through than you wanted to. get more air than you want it to, it's going to go around the system and cause the turbo to spin up even faster. Like, well, I didn't want what I just got. Now I got more. So that makes a problem. So see, if the differential controller was not operating, any increase in throttle would cause an increase in turbo speed. This increases, turbo speeds up, which causes more upper deck pressure. More upper deck pressure leaks across the manifold, the plate, manifold, throttle to give us more.
Exhaust out of the cylinder.
Well, it goes across the throttle plate into the manifold. Now we have more pressure in the manifold. More pressure in the manifold means
Exhaust back to
more exhaust back turbo. Now the turbo speeds up more. So it's like you didn't want all that. So
Runaway.
yes, a runaway. So bootstrapping, kind of a runaway process. Overboost is a lot easier to understand because the name is very clear. That is when you overboost an engine. So there are manufacturer's limits to what you can have for overboost. So overboost is when manifold pressure exceeds manifold pressure. Manifold pressure. It's even more pressure than before. So now I got to take time to erase that. See, try and save time. Didn't work. When manifold pressure exceeds manufacturer set limits. Okay, good. I was going to say there's overboost and overshoot. I hope I talk about overshoot. Yes, so overboost. See, it can happen due to the time it takes for all these components to change. You're not paying attention. It takes a while for the controllers to do their thing, and you just slam the throttle forward and like, whoa, that was an overboost. So you have to watch out for overboost. And then there's overshoot. Overshoot is less. It's just a momentary. It's a momentary overboost due to a lagging system. Overboost is when you actually go beyond what you're supposed to and it runs there for a while. I was trying to think of the time. It's like 3 seconds.
That's a short time.
It's a short time.
It's not like
Yeah.
cruising for.
Well, there's a service bulletin, and I think I have it in here. Let me see if I do.
It's not like an actual turbine where it's speed up
There we go.
millisecond.
No, that is not it.
It's like a hot start in a turbine. Going to the red for 1 second, you know, check it.
Yes.
2 seconds, check it. 3
Yeah,
seconds,
but it's still,
whistle.
but that still seems more sensitive than this.
Yeah, so I thought I had overboost numbers in here. Let me see.
Is it like a turbine where if you overspeed it, you have to do a check?
Yes.
So if you
So-
overspeed it even for a second, if you overshoot it, it requires an inspection?
I guess I really thought I had.
No, that's so.
I really thought I had those in here, but you know what? I think that it comes from. We actually talked about overboost when we did engines. That's where we talked about it. So we already had the inspection. There's a service bulletin. We talked about it. How much? It was even a test question. How much time it was, but we seem to have all forgotten what that number was. It was 3 minutes, 3 seconds, something. Like I can't remember everything. It's late, man. I'm tired. So how do you know? Where are you supposed to go to find this stuff? If somebody overboosted their engine, where are you going to go to find out what to do? I mean, please tell me you're not going to go to YouTube, my class notes. Where are you going to go?
GCSD or something?
Service bulletins, service letters, service instructions usually have all of that information for the engine.
It's hard to remember where to go to.
Well, that's the thing. You gotta remember where to go to find you. I know, it's not easy. Okay, overshoot, that's a momentary overboost due to system lag. For example, constant speed props, you could actually hear this happen. So that'd be overspeed, but it's the same thing. I can have an overspeed or an overshoot. So if I take off on a constant speed prop and the governor's not adjusted normally, or somebody adjusted the governor to a tachometer, which is way off, and come to find out you've been running around at 200 RPM over this whole time, that would be an overspeed in that situation. So same thing with an overboost. You're running it for a little while in that position. An overshoot, and I can get an overshoot with my RPM because the oil's cold in the prop, and so I give it full throttle going down the runway. You'll hear props go past you can hear the RPM go up and then right back down. So it overshot but came right back in. Follow? So that'd be an overshoot. It hits a number but falls right back in line. Just watch it happen. That's not an overboost. So an overboost is going to be defined as something that kind of stays there for a while. So, all right, let's see. We have some other systems. We have the variable pressure controller system. Still a Lycoming system. All right, there we go. Lycoming variable pressure controller. Ooh, that's a very small drawing.
Even I can't see.
Yeah. Which one do I want to go to? Because I think there's two different types. We'll go with this simple one first. There we go. All right. Now, just by kind of looking at it, we should be able to figure out something. You probably, can you see the hand there okay? 'Cause I can't do the laser when it's big. All right. Air comes in the compressor. Goes into
Upper deck.
upper deck. And we have a,
Pressure relief.
all right, what's that connected to? Nothing. It's a safety valve, right? Okay. Right here's our throttle. So in our upper deck, we have a variable controller. Variable controller is connected to the upper deck. All right. And then we can see the oil in and out. So that's all this one is showing. But I think it's got a better one over here. So there we go. Our variable pressure is linked by a cam to the throttle. So as we increase throttle, it is going to is going to bring this cam around, putting more pressure on the system, asking for more boost. So let's see, we have, where's my air inlet? Find the turbine wheel. Compressor, air inlet, intake air. Oh, this is the sense line. A sonic venturi is for pressure, well, it says right there, cabin pressurization. So it limits the amount of air that can get into the cabin. But cabin pressurization is always run off a turbocharger. Anytime you see a piston engine with pressurized cabin, it's off the turbocharger.
No, every pressurized airplane is going to have turbo?
Any
piston-driven?
horizontally opposed piston-driven aircraft, yeah. I mean, older ones had like a Roots blower system, and all, they were different. But if it's piston engine contemporary aircraft, you got a turbocharger. Well, you're going up high anyway, so you can have a turbo. And that's the sonic venturi does that. So, all right, so this is just sensing it. So this controller is sensing strictly upper deck pressure. We got the throttle valve. Throttle valve goes to the engine. Out of the engine, it goes to here to the wastegate, to the Y, either out overboard or wastegate that way. Be cool?
Sure.
So it's one controller. It's got words. Spring and vacuum keep controller servo valve on seat, allowing oil pressure to build up and close wastegate. When deck pressure increases as a result, servo valve is raised, lowering oil pressure and regulating the wastegate. Operation is continuous and reoccurring. Base of controller moved up or down by cam for controlling of wastegate setting. So it's actually a pretty simple system because you only have this one controller. So that is, replaces the density / differential system. So now you just have one controller. It uses a cam. uses a cam linked to throttle to vary the pressure on a spring within the controller for optimum deck pressure at a given throttle setting. Good with that?
Yep.
Okay. This one sort of pisses me off. I have worked so hard to figure out what a slope controller is and how it works. I have read everything that I have. I have read more stuff. Some stuff I can find is conflicting. And then it comes down to it is similar to a differential controller. It is connected, and so it means it's connected across throttle plate. And it's almost like what happened is they took the system with the two controllers, ripped out the density controller, left one alone, and said, let's rename it. It's called slope control because it does the exact same thing. And so I believe that, and I could be wrong, if you have a slope controller, or in other words, a density controller, then you would also have a pressure relief valve in upper deck. That's all I got there. Obviously, it's going to have something in there that does a density controller, because at some point, your pressures are going to be near equal and it won't work well. But that's all I could find on that. So, but if you got the other one, the first one, you are doing good. And then we can talk about the TCM system. Thankfully, it's not confusing. Too much. Let's see. The typical system uses 3 different controllers. They are the absolute pressure controller, the rate of change controller, sounds like a question that Cooper would ask. If you had to be a controller, which one would you be? I would definitely be the rate of change controller.
What about an aircraft controller?
No, of these 3. These are my 3 choices. Pressure ratio controller. All right, it's almost this. It works the same way. You have the same wastegate, you have the same bleed system. You just have different names for controllers. So we've already learned how the system works, right? So I have to go through a whole new system. It's like, oh, this is completely different. Almost everything is the same. We just have to define these 3 controllers. So we can look at a drawing. What's this one? Oh, that's a slope controller. Hello, slope controller. It is across the throttle. Oh, it does have a pressure relief valve. Told you. So, told you. Piss you off. Okay. There we go. My TCM one. Engine oil comes in right down here. Goes to a wastegate. When pressure builds up, it pushes on the wastegate. that's going to cause it to close. And if you drain off the oil, it will open it up. So everything works the same. So oil comes through here, comes to this side, and we have our controllers. So are the controllers in series or parallel? Well, let's see here. This one is there. That is kind of series, but this way goes parallel to that way. So it's kind of a series and parallel. I know. But it can go this way, up this way, and that way. Okay, first thing we want to notice is every single one of them is vented to
Upper deck pressure.
upper deck pressure. Okay, so everyone's vented to upper deck pressure. A, because it says right there, A, down here, pressure ratio controller. So, let me see. Pressure ratio controller is going to control, as you can see in the drawing, it has an opening here, and it's connected there. So it is monitoring the ratio between ambient and upper deck. If that pressure gets to be too much, it is going to open up and bleed off oil. It does not, it's set to a certain limit between the two. So what happens is if you go very high in altitude, at some point, an engineer has figured out if you have a very low outside ambient pressure and you're pumping this much air into the upper deck, then you're going to have too much of a split, which is going to mean the air is going to be too hot, if nothing else, too hot. And you're going to just see the design limits. You can start blowing off hoses. So that will take care of that. Then we have B, which is the rate of change controller. So I don't even know if I have notes here on this. Rate of change controller. It senses the rate at which this is taking off. So if your turbo is spinning up fast and that pressure is coming on, this thing's going to go, wait a minute. I know what's happening next. We are going to overboost or overshoot. So this starts shutting it down right then before that happens. Okay? Then we go into C, the absolute pressure controller, which absolutely controls it. It's designed to limit the maximum upper deck pressure.
Sounds familiar.
Yeah, so a lot like the pressure ratio, or the density. Yeah, so it's going to check the density. So that's it. That's how they work. Now I can write some notes. All right, so let's see. Of my three, let's see. Let's see. 2. Absolute pressure controller. Absolute pressure controller. Let's see. Designed to limit maximum upper deck pressure. Max upper deck pressure. UDP. Upper deck pressure. So obviously at a set limit, the valve will bleed off oil. And to work to the wastegate, open wastegate, slow down the turbo. That's it. We have the rate of change controller. Senses the rate at which upper deck pressure increases. If rate is too fast, valve opens and bleeds off oil, which causes wastegate to open and slows the turbo. And then we have the ratio controller. So at higher altitudes, the turbo must work hard to keep manifold pressure set for max horsepower. So remember, we got this absolute pressure that is always asking for more turbo. So if it was left up to that, we could go as high as we wanted to, and this thing would just spin up faster and faster and faster and just keep pumping more air in, right? Doesn't matter how hot it gets, it's just going to keep going because it knows one thing, it's got to have more air. So we get to a point where the ratio controller is going to say, yeah, you know, at this altitude, we need to start backing off. So to me, that's kind of where it's going to set its critical altitude for this engine. So at high altitude, the turbo must work hard. The turbo, it works hard. I'm not going to, it works extra hard. Hard to keep. Manifold pressure set for max power. Right? That's its job. At some point, air becomes too hot and could cause detonation. So ratio controller, we'll make that A, make this B, ratio controller. Keeps this from happening. Keeps this from happening. Let's see, senses upper deck pressure and ambient. And limits UDP to 2.2 times ambient. All right, everybody caught up with me? It's the same operation. Do I need to leave it on the words? All right. So, engine's off. We get in the airplane. What position's the wastegate in?
No oil pressure says open.
Right.
Yeah.
Spring loaded to open. Right? That's our default position, open. If everything went to hell, you don't want the turbo spooling up.
Faster.
Yeah, all the way. So default's going to be open. That'd be safe, no turbo.
Yes.
I know it's hard to think about it. Well, would it be safer to have no turbo or all the turbo? I guess they figured it'd be safer to have no turbo than all the turbo, because when you lose a turbo, is that an emergency?
No?
You just became a normally aspirated engine.
Oh, that sucks.
Yeah, although I was listening to a story about a guy who lost a turbo and ended up losing his engine, but he lost the turbo, and his comment was, it was no big deal. It's happened to me before. I just became nothing more than a normally aspirated aircraft. I was finishing my flight. We were close enough to the airport, but what he didn't know is the turbo failed because a line blew off because somebody didn't tighten it all the way. So what happened to all the oil in the engine?
Went back to the earth.
Yes, it was direct recycling. Went to the earth, so engine lost all its oil pressure, seized up, and they crashed. Or he made it. I don't remember what. So, okay, engine's off. Wastegate is in the turbo off position. We start up the engine. Oil pressure is going to go to the wastegate, flow out the wastegate to controller. What are both controllers probably going to be saying at that point?
We need more power.
Yeah, we got nothing here, pal. So they're going to close off. Definitely the absolute going to close off. And the differential, or the rate of, in this case, we'll talk Continental, the rate of rise, what's it thinking?
There's no right.
We're fine. We're just idling. So it's closed. Absolute's closed. And the ratio controller is also saying it's 2.2 times.
Yeah.
It's
Ratio
low.
control or the, oh yeah.
Yeah. So all three of them are in agreement that more turbo is okay.
Yes.
Blocks off the oil. Wastegate then starts to close, spinning up the turbo, and it's going to do that until which one's going to be the first one to kick off.
Rate of change.
I think the rate of change is really more of a kind of a fail-safe. I don't think that one happens unless you mash the throttle forward.
So absolute.
So probably, I think the absolute's going to be, I think it's going to be the pressure ratio. It's going to be the first one to kick off. Because remember, absolute wants
The most.
full power, and I'm idling. Rate of change, that's not going to be unhappy at all because I'm just idling, so I didn't mash the throttle. So it's going to build up until I get to the pressure ratio, 2.2 times, and it's going to be like, oh, that's enough here. Which is a lot like the one that went across, the Lycoming that went across the two, which was the pressure ratio. So again, it's a ratio. So I think the first one will be ratio, right? So I take the runway and I mash the throttle forward. Where I gotta go? Which one's going to be pissed off next?
Rate of change.
Rate of change is going to start. It'll allow it, but it's going to start bleeding off here. You got to slow down here. Okay, then the turbo kind of stabilizes. Then the rate of change is going to now close, right? Okay. Pressure ratio is going to be kind of fluctuating because we're climbing. It's going to be okay, a little more. No, we're fine. A little more, we're fine. A little more, we're fine. Until we get to a very high altitude where it's going to. Yeah, it's going to pretty much, let me think.
Stay open when shoots are high.
Yeah, when it's going to stay. I was trying to think of when is the absolute pressure going to come on there. Actually, we mashed the throttle forward. That thing probably got pissed off too. Yeah. Yeah.
Whoa there.
Let me see. Let's see. What do I have? Engine started. Let me see. Absolute pressure bleeds off. Let me see.
Alright, piece of gun.
All right. Oh, so I do have this number. Let's see. Rate of change. Rate of more than 6.5 inches per second. So that's 6.5 inches per second.
Yeah, that's actually wow. Holy shit.
So if I went through all my notes through the whole system here, and I wrote, let's see. Oops, we're on page 23. There we go. Okay, so engine off, wastegate, spring loaded to the open position, turbo's off. When the engine is started, oil pressure sent to the wastegate closes and spools up turbo. Upper deck pressure and manifold pressure increase until absolute pressure controller opens. So according to my notes, absolute pressure will be the first one to open. Opened absolute pressure controller bleeds off oil in the wastegate, causing turbo slow and stabilize upper deck pressure. If upper deck pressure increases a rate of more than 6.5 inches per second, the rate of change controller opens. Bleeding off oil and slowing turbo. This prevents overboost and overshoot. We knew that. At about 16,000 feet, the pressure ratio controller unseats and starts bleeding off. So 16,000 feet becomes known as our critical altitude. If the fuel injection system uses a variable orifice fuel pump, I don't think any of you guys, we haven't had anybody do that one, but you can have a variable orifice fuel pump on your Continental controllers. So the high-speed needle can be attached to a bellows attached to upper deck pressure. So when you hit the throttle forward and the engine speeds up, it's going to speed up the pump, which is going to want to deliver more fuel. But the turbo isn't finished spooling up yet. So if you reference that aneroid, that bellows, to upper deck pressure, it will stay open, allowing more fuel to recirculate through the Continental pump. Then when the turbo spools up and upper deck pressure acts on the bellows, then it will close the high-end orifice, causing more fuel to go out to the engine. Did I say that right? Let me see. Yeah. If the fuel injection system uses a variable orifice fuel pump, low manifold pressure will reduce fuel flow during acceleration until manifold pressure is increased. This prevents an overly rich mixture due to turbo lag. Yes. There are some other TCM systems, which I'm not going to get totally into. I would just tell you There's the variable absolute controller.
Is the rec room over there still open?
I can open it.
You mind if I go over there real quick and just get something?
You got to grab my keys off my desk. The red lanyard. That's all 3 controllers into one unit. It also, just leave it at that. And this one also has a slope controller. I think they just both threw that in there. I talked about intercoolers briefly. What's an intercooler? Okay, this air gets hot. So you run this air through a radiator. And so this is cools air after it leaves the compressor. Cools air after it leaves compressor. If you cool it, you get back some of your density. Wow, I don't know if I should. I hate to rush through this. So for some maintenance needs, you're gonna have to write this down. These things get sticky. Oh, there was my thing. Intercooler, you're gonna look for damage on your fins just like you would a car. Bent fins means you don't get air through it. You don't get air through it, it's not working. Mouse milk is what we use to lubricate wastegate components. You have to keep them lubricated because they get really rusty and nasty because of their environment. So going to put some mouse milk on that. Let me see. Keep our induction clamps tight because you are prone to more induction leaks because of all the pressure. Do not adjust controllers. There are adjustment knobs on there. I have never had to adjust a controller. When I went to Lycoming school, they just went on and on about not touching. When you have trouble and you call troubleshooting, the first thing they might ask you after they get all the information, what have you done to the controller so far? And I think once you say you touched it, they're going to say, well, best of luck to you. To adjust the controllers, you have to have a lot of setup equipment. You have to know the current, well, it depends on the atmospheric pressure and stuff. So you need exact instructions and exactly what to do. It's not something you can just like a carburetor. Well, I'm going to back this out and do that. Nope, don't do that. So,
For any controller?
yes, all of them. Don't touch them. We talked about the V-bend clamps. We talked about pressurization. Comes off the turbocharger. What's that item where the pressurization comes off the system? It goes into the cabin?
Oh, the Sonic.
Sonic Venturi limits the amount of pressurization that can be stolen. Let's see. Oh yeah, so if you have a turbocharged system and a pressurized cabin, you're probably also going to have pressurized magnetos. Remember talking about that? So upper deck pressure is going to be vented to the magneto. So they changed out the plugs on them so they hold a little more air pressure, but it still has to flow. It's hard on the magnetos because that air is kind of nasty, even though you're using it for the cabin. And then I threw this slide in here because I think there may be a Q&A question about it. Called a power recovery turbine, PRT. Also called a turbo compound engine. There was a funny story I read, and the guys that used to work on these, they were on radial engines. The PRT stands for? Power Recovery Turbine. They called it a parts recovery turbine. So, just after World War II, the Wright R3350 18-cylinder aircraft engine used 3 turbines to recover 20% of the exhaust energy in a Douglas DC-7 and Lockheed Super Constellation airliners. Early designs were a failure and called parts recovery turbine by the mechanics. Auto manufacturers were looking at this concept. I think Detroit Diesel did it. Ferrari had something. But what you have, just by looking at the diagram, is here's our crankshaft, and that represents what kind of engine is this? A lawnmower engine. No, it's a radial. So radial engine. off the back of the radial engine. In the accessory case, you're going to have a gear that's going to drive another gear with a fluid coupling. So that tells me that it's kind of like a, well, I shouldn't use this one, but I was going to say an automatic transmission has the torque converter. So fluid-filled coupling, so there is some slippage there should you need it. That then is, well, I'm doing it backwards because I'm saying this doesn't drive that. It actually starts up here. Exhaust gases go this way. They go through these turbines, generating power in the turbines, which runs down the shaft, which then spins these two gears, which spins a fluid coupling, which drives against this gear, which is attached to the crankshaft, spinning the crankshaft, adding about, how much, what percent?
20%.
Yeah, so. So, all right, that was kind of fast. I hope I didn't break anybody. So, test tomorrow?
Sure.
Okay. So, we talked about magnetos. You better really be up on your magnetos because there's a lot of magneto questions.
We're ready.
Okay.
We're ready.
All right. Atmospheric pressure on a standard day.
29.
All right. I have a couple of gas questions in there about what happens when the gas expands, container, that kind of stuff. Should be able to define manifold pressure versus upper deck pressure, and what happens to those. Let me see. Ground boosted engine does what?
Add manifold pressure above sea level.
Manifold pressure above sea level. Critical altitude is what?
The point at which it starts to lose power.
Lose power. Okay. No, not lose power.
You're
You're not wrong, but you're not right.
When it gets to
Go below.
normal sea level pressure is at a certain.
Yeah.
We're no longer at sea level pressure. Let
Pressure should
me
drop.
see. What's the main limiting factor in increasing manifold pressure? Why can't we just keep on going?
Heat detonation.
Heat, and that reads to detonation.
Bad things.
Does a turbine compress fuel and air, or just fuel, or just air?
A turbine?
Yeah, turbo.
Oh, I think about the turbine. I was like.
The whole assembly, the compressor side. Compressor side. Fuel and air, just air? What about an internal supercharger? Fuel and air, okay. What drives internal supercharger?
The engine. Gears.
Gears. What drives a turbocharger? Okay. All right, you better know how those wastegates operate. And as far as memorizing controllers, yeah, we talked about the density pressure. So the two systems that the test questions would be based on would be that one. I would know all three of those and what they do. The TCM and that one. Differential and density. Cool. What's the maximum temperature that evaporation ice can occur?
100 degrees Fahrenheit.
Damn. What pressure do we check exhaust systems at? How many PSI?
15?
That would be bad. That's a lot.
What do you mean would we check the?
Exhaust. When you do the soap test around exhaust,
Oh.
how many PSI?
Yeah. Whatever vacuum can put out. Like
Would you? About
25?
3 to 5? 2? 2? Okay. I'd go 2. 2. When is ice most likely to happen in a carburetor?
Where or when?
What operation of flight?
Landing or idle? Low power.
Low power, landing or idle. Oh, that was it. Okay, so I guess you can go.
See you tomorrow.
See you tomorrow.
Oh yeah. Let's do that tomorrow.
Just a heads up, sir. Austin and I are probably going to be a little bit late.